Hi everyone, this is the first lesson video of Chapter 4, and we're going to start talking about quadratic functions and transformations of quadratic functions. So our objective for today is that we can identify and graph quadratic functions. So let's begin by defining what a quadratic function is. It is a function that you can write in the form f of x equals ax squared plus bx plus c, where a does not equal 0. If a equals 0, then that would cancel out the x squared term, and then we would just be left with a linear function, which would be completely different. So you do need to remember that the biggest exponent for a quadratic function is 2. So x squared will always be part of the equation of a quadratic function. When you graph a quadratic, it graphs as a parabola, and a parabola is a U-shaped graph. You can see it opens up for the first one that I drew, and the other one is opening down. The form f of x equals ax squared plus bx plus c is known as the standard form of a quadratic function. The form that we're going to be focusing in on today during this lesson is vertex form. So that form is f of x equals a times the quantity of x minus h squared plus k. And again, a must not equal 0. So the benefit of vertex form, you're probably guessing it already, is that it'll be easy to graph because the vertex will be given in this form. Now let's discuss a few other key terms and then we'll practice graphing. The axis of symmetry is a line that divides the parabola into two mirror images. So if we were drawing the axis of symmetry for the two basic parabolas I drew above, the axis of symmetry would be going right through that point at the bottom or at the top, which we'll later learn that those are called min and then max. And actually the min and the max, those are called a vertex. And the vertex is in the form h comma k, so it's a coordinate. And the vertex is the point where the parabola intersects its axis of symmetry. It's also the place where the parabola changes direction. So here is the parent function for a quadratic function. It is the equation f of x equals x squared. Just to remind you, f of x is function notation, and that just stands for y. So the input is whatever number you're plugging in for x. So the equation for the parent function is f of x equals x squared, and it is the parabola shown below in the picture. It goes through the origin, that's the vertex, and the axis of symmetry is x equals 0, or also known as the y-axis. So when we're graphing quadratic functions today and beyond, we're really just transforming the graph of the parent function. And hopefully you remember all the transformations that we have learned in the past couple chapters. We will be using that knowledge today. In example 1, we're going to learn how to graph a function of the form f of x equals ax squared. So it's going to be the parent function, and it's just going to have a either stretch or compression because we have that number in front. Multiplying the x squared. So step 1, we want to plot the vertex. And we know the vertex is at the origin because there's no other values after the x squared. So let's plot the vertex and also draw the axis of symmetry, which is the equation x equals 0, or the y-axis. Now that we have the vertex and the axis of symmetry plotted, we want to find and plot 2 points on one side of the axis of symmetry. So you may be wondering, how do you choose which points to plot and which points to use in the table? What you want to do, once you find your vertex, you want to choose 2 points on one side of the axis of symmetry that will give integer values for the output f of x. So in this case, since we have a fraction 1/2 in front, it would be a wise idea to plug in even numbers for x. So I'm going to plug in 0, 2, and 4. When substituting in the values 0, 2, and 4, I got my output values as 0, 2, and 8. So the coordinate points that I'm plotting are the origin, which is already graphed, 2, 2, and 4, 8. And you are probably noticing that since I would run out of room on the graph, I went up by 2's on the y-axis. So I plotted those 3 points, and now what we want to do is plot the corresponding points on the other side of the axis of symmetry. So you basically just want to count how many units away horizontally is each of the points from the axis of symmetry. So you can see right here at the coordinate point 2, 2, we are 2 units away from the axis of symmetry. So I need to count 2 units to the left to basically mirror or reflect on the other side. And then for the coordinate point 4, 8, I am 4 units away horizontally from the axis of symmetry. So now I'm going to count 4 units left of the axis of symmetry to reflect. So we have those points plotted now, and now we just need to connect and sketch the curve. So here we have the graph of f of x equals 1/2 x squared. Now we're going to formally discuss the transformations, reflection, stretch, compression, all of those that we have discussed in the past. We're just going to apply them to parabolas now. You probably remember that the way that you figure out if the curve opens up or down is the a value. So if the a value is positive, it is opening upward, and if the a value is negative, it's opening downward. So you can see in this first picture that's what's happening. And then now take a look at the bottom half of the page. This is two graphs of parabolas on the graphing calculator, and like we were saying, if the parabola opens upward, then we have the a value being bigger than 0, and the vertex is the minimum of this graph. And the converse of that would be the a is less than 0, the parabola would be opening downward, and the vertex would be the maximum of that parabola. Now let's talk about stretching and compressing. Hopefully you remember that the a value not only determines if it opens up or down, but it also determines if the curve is going to be stretched or compressed. So it is stretched if the a value is bigger than 1. So that means, any number is bigger than 1. 2 is an example in this graph here. And if the number a value is bigger than 1, then the graph is going to be stretching vertically and narrowing horizontally. And for a compression, the a value is between 0 and 1, so a decimal or fraction between those two bounds. If the a value is between 0 and 1, it's going to be compressed vertically and widening horizontally, as you can see in this picture. In example 2, we're going to learn how to graph translations of the parent function f of x equals x squared. So let's begin by taking a look at part A, g of x equals x squared minus 5. So we want to draw the parent function that goes through the origin, as we discussed earlier. And the parent function goes through the origin, and then the way that you can figure out the other values, you can go up 1 over 1, and then from there up 3 over 1. And if you forget that these are the patterns for the parent function, you can always just make a little quick XY table on the side. And instead of making them solid, because this is not the actual graph, I'm going to make it dashed. Okay, so we have the -5 after the x squared. That means we're going to be shifting the parent function down 5 units. So each value of x, the value of g of x, is 5 less than the value of f of x. So now the vertex is going to be at the coordinate 0, -5, and we're just going to be counting down 5 from each of the original points. And you can connect with a solid curve. The directions asked us to not only graph each function, but also describe how each graph is a translation of the parent function. So what you want to write is that we translated the graph of f of x down 5 units to get the graph of g of x. For part B, we have the equation h of x equals the quantity of x minus 4 squared. So this time the number is inside of the parentheses, so that means we are changing the x values rather than the y values. So hopefully you remember that when it appears as a negative, so -4, we're actually going 4 units to the right. And the reason why is because that minus sign is part of the general form. So we want to count 4 units to the right of the parent function. So the vertex of our parabola is at the coordinate point 4, 0, and our axis of symmetry is at the line or equation x equals 4. So again, we translated the graph of f of x to the right 4 units to get the graph of h of x. So we just practiced translating down and translating right. I'm going to assume that you should be able to do the other 2 directions as well. So let's talk a little bit more about vertex form. Remember, we talked about this at the beginning of the video. The equation is f of x equals a times the quantity of x minus h squared plus k. The nice thing about vertex form is that it gives you the information about the graph of the f without drawing the graph. So if a is greater than 0, the k is the minimum value of the function, and vice versa. If a is less than 0, k is the max value. We recently discussed that the a value determines if the parabola opens up or down, as well as determines if it's stretching or compressing. The hk The h is the axis of symmetry, so the equation would be x equals h, whatever number is in the h spot, and the numbers in the h and k spot determine what the vertex is. So you can take a look at the two graphs below. We have f of x equals 0.5 x squared. That is currently in standard form, but if we were to change that into vertex form, it would be f of x equals 0.5 times x minus 0 squared plus 0. And the reason why I'm putting those zeros in there is because the vertex is at the origin. And a similar thing applies for the next graph. We have the standard form f of x equals negative 3x squared. If we were to change that to vertex form, that would be negative f of x equals negative 3 times the quantity x minus 0 squared plus 0. So you can see in the equation and the graph as well that the vertex is the origin for both of these. But that will not always be the case. Example 3, we're going to learn how to interpret vertex form. So we're given the equation y, or f of x, equals 3 times the quantity of x minus 4 squared minus 2. We need to determine what the vertex is, the axis of symmetry, whether it's a minimum or maximum value, as well as the domain and range. So first off, let's just look at the given equation and compare it to the vertex form. So I rewrote the equation as well as the vertex form directly below to make sure it's super clear what the a, h, and k values are. First off, we know that the vertex hk is the coordinate 4, negative 2. And I'm getting that from the highlighted pieces right there. The negative sign inside the parentheses is built in, so you don't include that in the coordinate. However, the minus 2 for the k value is included because in the vertex form there's a plus sign there. So now let's take the axis of symmetry from there, and you basically just take the x-coordinate of the vertex, which is 4. So that means our axis of symmetry is the equation x equals 4. In this particular equation, the a value is positive 3. Because this a value is greater than 0, the parabola is opening upward. That means our k value, or negative 2, is the minimum value, and that's because the parabola is opening upward, so the vertex is going to be at the lowest point of the graph. For our domain and range, remember domain are the x values and range are the y values. For a parabola, the domain of a parabola is always all reals, unless there are certain restrictions, but typically there are no restrictions. So that's why the domain of this parabola is all reals. For the range, there are restrictions because since the negative 2 is the minimum value, that means there are no other numbers below negative 2. So you want to write for range all real numbers such that y is greater than or equal to negative 2. Let's talk a little bit more about transformations when using vertex form. So you stretch the graph when the absolute value of a is greater than 1, or compress when the absolute value of a is between 0 and 1. You reflect the parabola across the x-axis when a is less than 0, aka negative numbers for the a value, and you translate or shift the graph, the absolute value of h units horizontally, as well as the absolute value of k units vertically. So below in the key concept box, you just have a visual representation of what we were just talking about. Horizontal shift means you're going left or right, and the vertex will be changing the x-coordinate. And for vertical shifts, you would be moving it up or down, so that means the vertex, the y-coordinate of the vertex is changing. And then for horizontal and vertical, that means you're doing a combination of both directions, vertically and horizontally, and that means the vertex is changing depending on in what direction you're going. Here in example 4, we're going to use vertex form to graph the equation f of x equals negative 2 times the quantity x minus 1 squared plus 3. So I immediately wrote vertex form directly below to make it easy for us to figure out what the a value is as well as the h and k. So I know that a is equal to negative 2, which means the parabola is going to open down and we're going to be stretching the parent function by a factor of 2. I also know that the vertex is going to be at the coordinate 1, 3, because the values of h and k respectively are 1 and 3. Now that we have identified the constants, we can plot the vertex and draw the axis of symmetry, which I have done in the graph at right. I chose two values for x that were to the right of the vertex, so I chose 2 and 3, and when I substituted those values in for the equation, that we were given, I got the coordinate point 2, 1 and 3, -5. So I'm going to plot those now. And then to get the other side, you just want to reflect. So like I talked about in a previous example, you just count how many units away each coordinate is horizontally from the axis of symmetry. So we want 1 point to the left here, and then 2 points to the left here. And then you want to connect. Part B is asking us what steps transform the graph of the parent function to the graph that we just went through above. And these are the steps that we took. We stretched by a factor of 2, and we also reflected across the x-axis. Both of those steps were determined by the a value of -2, as we discussed before. Also, the vertex coordinate 1, 3 had us translate the parent function 1 unit to the right and 3 units up. We can use the vertex form of a quadratic function to model a real-world situation. So before we do that, if you could just write at the top, "Hi, Mrs. Allen," next to example 5 so that I know that you're listening to this video, and thank you so much. Okay, so here's example 5. The picture shows the jump of a dolphin. What quadratic function models the path of the dolphin's jump? First thing we want to do is determine what the vertex is of the path of the dolphin. So we can see here I plotted a point on the graph. The vertex is at the coordinate 3, 7. So that means our h is equal to 3 and our k is equal to 7. Now we want to choose one other point from the curve, and in this case we're choosing the coordinate point 9, 4. And that will help us in the process of writing the equation. So I wrote down the vertex form that we've been using in this lesson, and I also substituted in the values of h and k that we just found. The other coordinate that we're using, 9, 4, I wrote on the graph, and I also labeled it x, f of x. So what we're about to do is substitute in the 9 for the x and the 4 for the f of x. Remember, f of x is just another way to say y. The only variable that we don't know, or rather constant in this case, is the a. So that's what we're about to determine. So everything else drops once we plug in 9 and 4 for x and f of x respectively. And then now we just want to do a couple algebraic steps to get the a by itself or isolate the a. Okay, so what I did there was I basically used order of operations. So I did 9 minus 3, which is 6. 6 squared is 36. I subtracted the 7 to the other side to get -3, and I divided by 36. And when I reduce that, I get an a value of -1/12. So now all we need to do is paste that in for the original form, and then we'll have the equation for the path of this dolphin. The equation that models the path of the dolphin's jump is f of x equals -1/12 times the quantity of x minus 3 squared plus 7. Here is the lesson check for section 4.1. They are very similar problems to the examples that we went through together. So write these down, show your work, including the graphs for those that request it. And please let me know if you have any questions the next time we meet. I know there was a lot of material in this one, but I hope that a lot of it came back from previous chapters so far this year as well as Algebra 1. Have a nice day.